Hey guys, this is Mr. Sal. Go ahead and take, I guess, about 1 minute and try out this bell work, then we'll go over it. All right, so for this first problem, 24 minus 7, you can stack that and subtract if you need to. It's just the 4 minus 7, you got to borrow from the 2. 14 minus 7 is 7. Drop the 1, get 17. Boom, there's your difference. For number 2, if you're doing this by hand, you got to force the denominators to be the same. And I know 6 is a multiple of 3, so I would just take the 3 and multiply it by 2. But if I do that, it will force the denominator to be 6. But I need to maintain the same value of the fraction, which is 2/3. So I got to multiply the numerator by the same factor there. So 2 times 2 is 4, makes that 4/6. Now plus 3/6. And the answer for this one is still being 6 because the denominators are the same, but then we add, in this case, the two numerators. 4 plus 3, and I get 7. So 7/6. Of course, if you wanted to change that into a mixed number, you'd get 1 and 1/6, but I'm okay with the improper fraction on this. All right, here's our objective for today. I can find probabilities of simple and compound interest. Of course, this is just the first part of the lesson today. We'll have a second part of the lesson after this objective is finished. But take 30 seconds and copy this down, please. All right, let's go ahead and get started then. So last time we learned about experimental and theoretical probabilities in addition to the fundamental accounting principle. So if we wanted the probabilities of these events, and we'll assume that everything's fair, not only the coin and the dice, but even if we combine the two coins and dice on this. So flipping a fair coin, this one only has, it's not even a compound probability on this one. And these are all theoretical because we're not actually flipping any coins or rolling any dice. But if you wanted to find the probability of landing on tails, and remember, this is how we would write this probability like this. And sometimes people just use the T here instead of writing tails, and that would work as well. But I put the full tails right there, just, I don't know, because I felt like this is early in the lesson and it should help us. Okay, so the probability of flipping tails on a fair coin. Now a coin, it only has two sides, right? So we're gonna show this as a fraction. We'll show it as a decimal and percent for this one. So since it only has tails or heads, that's two possible outcomes right there. Of those two, tails is one of them, so that's 1 out of 2. If you put this in the calculator as a decimal, you'd get 0.5, and then we know how to change that into a percent. You'd move the decimal 2 times to the right, and you'd get 50%. Okay, so there's the fraction, the decimal, and the percent for this one. That works out pretty good. So number 2, rolling a fair dice and landing on 4. So we'll just write this as the probability of 4. You could write landing on 4 if you'd like to, but this is a function for us, which is nice. It's in function notation because P will represent a probability, and it's always capitalized, just like we've learned. So the probability of landing on 4, right? Well, let's just show the fraction for this one. Of course, you could change it into a decimal and a percent. If you change this one into a percent, you'd probably want to round it to the nearest tenth of a percent, which I believe it will on the homework. So a dice, of course, is a cubic shape. So that would give us 6 total possible results. So that's our denominator. It's out of 6. And 4, if it lands on 4, of course, you have possibility of landing on 1, 2, 3, 4, 5, or 6. So these are our 6 possible outcomes. 4 is one of those. So that would be 1 out of the 6 possible numbers that a fair dice can land on right there. So that's 1 out of 6, which I believe as a decimal is 0.16 repeating. So as a percent, it'd be about 16.7. If you round to the nearest tenth anyways, 16.7%. Well then, what is the probability if I flip a coin and roll a dice that I land on tails and get a 4? Now what we're looking at here is a combination of the two that we just found, right? We want to know tails and get a 4 though in this case. So try the probability for this, which would be considered a compound probability. And that's because we're going to not only find tails, so I'm just going to use T for tails, but also we want to find a probability for 4. So we're now combining two different events on this one. And here's what we know, right? we know the probability of tails up here was 1 over 2. So I'm going to write that as a fraction. This is just for the tails part. So I'll go ahead and write that in. This is just the probability of getting tails. But then we want the probability of getting or rolling a 4 on a dice, and we see that probability right here is 1 out of 6. So I would write that in, 1 out of 6, which is the probability of rolling a 4. And yeah, these are probabilities. You could even write that as the two separate ones, right? Probability of tails right there in purple, and now we have the probability of rolling a 4 in green. So to find the overall probability of these two happening together, if we combined the two events, all we would need to do is multiply these two fractions. Now, of course, you could type that into a calculator. I think this one's easy enough that we can do it directly, because in the numerators you'd have 1 times 1, which is 1. In the denominators, 2 times 6, which is 12. So this is 1 out of 12. And for this one, I'll go ahead and write the decimal for that. 1 divided by 12 in my calculator. And I get 0.083 repeating. That's easy enough to show, but if I wanted to round this to the nearest tenth for a percentage, it'd be 8.3%. But the fraction should work for this one, but just in case they do want a decimal. Of course, they should say they want it rounded somewhere in the assignment if it does want a decimal, but if it wanted the percent, it usually asks for it rounded to the nearest tenth. Now, just so we're on the same page, of course, to find the denominator here, you could have used the fundamental counting principle, which essentially we do when we combine these, because, of course, the coin would have had 2 outcomes and the dice would have had 6 different outcomes. Just multiply those two, and remember, that's the whole point of the fundamental counting principle, is that it helps you determine how many possible outcomes are available when we look at 2 events occurring in succession. All right, so simple events are pretty much everything that we've covered so far. It's like when we look at an experiment, but it happens pretty much one at a time, but it also has a single outcome each time, right? So when you flip a coin, it can only be heads or tails. When you roll a dice, it can only be 1 through 6. It's not possible to have 2 different outcomes happen at the same time. So that'd be like the first 2 examples that we did on that last slide. And then number 3 is what we call a compound probability, which we'll see later on in this lesson a little bit more. But I've kind of already explained how it works as well. So hopefully that made a little bit sense, but we'll see more examples to help. So simple event probability is just where we're finding the probability of that one thing happening based on whatever object we're using or whatever experiment we're performing. Now, just so you understand, that's just a little bit of vocabulary. I don't use this terminology very often, so if you're wondering if you have to have that memorized, you do not. And no, I will not be using this vocabulary either. We're just going to be solving for the probabilities. So right here, again, I don't really care if they're simple or compound probabilities. We're going to solve these either way, all right? And we may use the fundamental counting principle. I don't think we will, or that we'll need to on this one, but it may help us as well, okay? So let's find the probability. Number 1, find the probability of rolling a 5 on this. We'll say it's a fair die, so we'll compare everything as though it is fair random, okay? And that way we're not overcomplicating this stuff. But it looks like we will write our answer as a simplified fraction. So the probability of 5. Now, remember, for dice, you can get 1, you can get 2, you can get 3, 4, 5, or 6, right? So these are all 6 outcomes for dice. And I don't mind writing those right now because writing 6 numbers isn't too bad, especially when we're using it for this many problems. Now, that means that the fraction will always be out of 6, right? But to roll a 5 here, I see that's only one of the possible outcomes, so that's 1/6. We've seen that fraction before. And again, this one only wants us to write our answers as simplified fractions. Now, the probability of 7, this one sometimes confuses students. Please do not let it confuse you. Remember, it's out of 6, right? Because you can either roll a 1, 2, 3, 4, 5, or 6. 7 is none of those. So this is just a 0 out of 6 fraction of a chance to get to roll a 7. Well, what about 3? To roll a 1 or a 2. Now, this is 1 or a 2, okay? So this is, it's still not necessarily a compound event. We're still looking at just trying to figure out, well, if you roll a dice, where's the possibility you get a 1 or a 2? Well, remember, you still got 6 possibilities, but 1 or 2, that's 2 different outcomes that could happen from this. So it's 2 out of 6, but of course we know this would simplify into a 1/3. You can use your calculator to do that. You can scale the fraction down by dividing these both by 2 if you'd like, but either way you'll end up with the fraction of 1/3 because we do want the fractions fully simplified. All right, now for some of these, especially while we're getting used to them, you may have to think about these a little bit, and we encourage that. But it may take you a little bit more time than you would expect in the beginning. But for the probability of not 6, right? Well, again, you're looking at 6 possible outcomes. But how many of those are not 6? Well, that'd be 1, 2, 3, 4, and 5. And that's 5 possible outcomes that are not 6. So that's 5/6 would be our fraction for this one. And you see, once we look at kind of in a not format like this one, then the probability becomes much higher. Unless unlike on number 5, when we start adding more values that it could not be. Now, of course, we're still looking at 6 possible outcomes, but we just removed 1, 2, 3, 4 of those, which leaves only that it'd be like saying, well, what's the probability? And this is the exact same thing. It's just said in a different way. What's the probability of getting a 2 or a 6, right? Because 2 or 6 is not part of this list. Well, that's 2 of the 6 outcomes, so that'd be 2, 6. Once again, we just need to simplify that, which we should always do for these fractions. It'd be 1/3. So what about the probability of 2 or 4? Well, again, it's out of 2. It's out of 6, but it's 2 of the outcomes out of the 6, 2 or 4. So that's 2 out of the 6 possible outcomes. Again, this simplifies into 1/3 for us. So I think about this too. If they had maybe included another number here, 1, 5, doesn't matter, but if they included another number here, then it would have been 3 different outcomes. That'd be 3 out of 6. We didn't see one of these that would have given us 1/2, but it's possible as well. So the fractions change depending on what it's asking for, but remember this p is a probability, which kind of makes this a function. Here's our next one. You have a bag of colored cubes, 12 red, 4 blue, 5 green, and 3 yellow. Find the probability of randomly pulling the given color out of the bag. Write your answer as a simplified fraction and a percent. Looks like we got both on this one. That's not a problem because our calculator will do the work for us. Okay, so the probability of green. So again, this is just one event right here. And looking at the values that we're given, we got 12 red, 4 blue, 5 green, 3 yellow. The first thing I would want to do actually for this one is figure out how many total cubes are in the bag. Okay, well, there's 12 red, we got 4 blue, 5 green, and 3 yellow. So that's 12 plus 4, that'd be 16, plus the 5 makes that 21, and then plus the other 3 makes that 24. So that's 24 total cubes. And why do we want to know that? It's because if we want to know the probabilities of these, we do need the total, because that's going to be our denominator on these ones. So the denominator is out of 24. And how many of those are green? Well, we see up here that it's 5 of the cubes are green, so that's 5 cubes out of 24. Again, we get to assume that this is being pulled randomly, which it did say right here. So 5 out of 24. The last thing we'd want to do is see if that fraction can be simplified. It cannot. So the next thing I'm going to do is put this into the calculator. 5 divided by 24, and I get 0.208 and 3 repeating. It said to round your answer. No, it did not say to round your answer to the nearest tenth, but I'm going to, okay? So this is for our greens. So again, as decimals, 0.2083 repeating. I'm going to round to the nearest tenth of a percent, which would be 20.8. And again, if you wanted to put the 3 repeating right now because it did not specify where to round, that'd be fine. But I'm going to round all these percentages to the nearest tenth if I need to. So there's number 7. So let's look at the probability of number 8 here, the probability of red or yellow. And once again, we still need the total number of cubes that are in the bag. We already know that there's 24 of them. Okay, so that gives us our denominator pretty quick. But we need red and yellow. And looking at this one, I see that there are 12 reds and that there are 3 yellows. So we would need to combine these in order to figure out our numerator. 12 plus 3 is 15. So 15 of the 24 cubes are red or yellow. And again, we're just pulling it out once, so it's technically a simple event. And I would think, well, could this be simplified? And if you're not sure if it can be, you could just plug it into the calculator and use the double arrow button to simplify that. Now, of course, you're always welcome to do this by hand if you'd like. I know they're both divisible by 3, which then simplifies this into 15 divided by 3 is 5 in the numerator, 24 divided by 3 is 8 in the denominator. And that would simplify our fraction 5/8. And let's see what that is in the calculator. 5 divided by 8. Enter 0.625, so that would be 62.5%. Remember, with that decimal, to change a decimal to a percent, you're just going to move the decimal 2 times to the right, and then whatever's left is your percentage. No need to round on this one because it was just 0.625. So 62.5% is our final percentage on this one. Let's see if I can make those a little bit more pretty. There we go. Well then, what's the probability of blue on number 9? So again, we got 24 total cubes on this one. And as much as we would want this probability to be 0, I see that there are 4 blue colored cubes in this bag. So we'll make this 4 out of 24. And yes, once again, this can be simplified. 4 and 24 are both divisible by 4, as it turns out. Again, the calculator would do this for you, but 4 divided by 4 in the numerator is 1. In the denominator, 24 divided by 4 is 6. So that'd be 1/6 as our fraction. And we've seen that percentage before, but I'm going to have to put it in my calculator again. 0.16 repeating, which then makes that, we'll make that, again, rounding to the nearest tenth, 16.7%. So what about number 10? Well, number 10 is the probability of not pulling a red cube out of the bag. So how many of the cubes are not red? Well, you got 4 blues, you got 5 greens, and you got 3 yellows. So once again, we just need to add these all together in order to figure out our numerator. The denominator will stay the same. It's still out of 24 cubes total. So adding these together, 4 plus 5 is 9, plus the 3 is 12. And yeah, you could have just said, well, couldn't you just subtract the 12 from the 24? Yes, and of course you'd get the same answer here. However you want to look at it, okay? So both ways work, but you get the same answer. Of course, this can be simplified. Both of those are divisible by 12. 12 divided by 12 in the numerator is 1. In the denominator, 24 divided by 12 is 2. So 1/2, that's an easy fraction for us. We should know that is already 50%. So there's our fraction and the percent. So what about number 11? The probability of blue or green or red. So we're looking at all 3 colors at the same time, but there's still only 24 cubes in the bag, so it's still out of 24 here. But how many blues are there? Let's see, there's 4 blues, there are 5 greens, and there's 12 reds. So we're going to have to add all these ones together to figure out this probability. And remember, this probability, by the way, before we figure it out, is the same thing as the probability of, looks like not yellow. These are the same, right? Because the only color that we have left over is yellow. So whatever this probability would be the same for both. 4 plus 5 is 9. 9 plus 12 is 21, is what I got. So that'd be 21 cubes out of the 24 are blue or green or red. And yes, this can be further simplified. 21 and 24, they're both divisible by 3. In the numerator, 21 divided by 3 is 7. In the denominator, 24 divided by 3 is 8. So 7/8. Again, putting this into the calculator, and we want the decimal, I get 0.875, but moving the decimal 2 times to the right makes this, well, 87.5%. Just got to move that decimal 2 times to the right, right? So 87.5 Squeeze that percentage sign in there, and there we go. So there's number 11, and then number 12, what's the probability of not getting yellow? Well, we actually just figured that one out, right? I didn't even notice number 12, but we figured that one out. It's the same thing as the probability of blue, green, or red. And, well, we already see that that was 7/8, which is the same as 0.875, so that'd be 87.5%. So no need for work on number 12 because we had already figured it out from this one. Just by making that comparison, I should have noticed number 12. But whether we did or not, you'd end up with the same thing because there's 4 blues, 5 greens, and 12 reds, which is still 21 out of the 24 cubes. So independent events, events that are not affected by each other. Compound events is just when we look at independent events that are combined. So that's like number 3 on the first slide that we saw, where we were tossing a tails and then rolling a 4 on a dice. They're 2 independent events, but we combine them, and that's what makes it a compound probability. So fill in the blanks for calculating the probabilities for compound events. In other words, for 2 or more events occurring together. And we shouldn't see more than maybe 3 or 4 events occurring together, but it's possible, especially when they give us the probabilities here. So suppose we call the first event A, whatever it is, the second event B, and the third event C, whatever they would be. Okay, it could be tossing a coin, it could be rolling a dice, it could be pulling cubes out of a hat or a bag, doesn't matter, okay? But the nice thing about finding compound probabilities, once we know the probability of each individual independent event, all we need to do is take the 2 values and multiply them, just like we saw on that number 3 from the first slide. So when it says what's the probability of A and B on this one, well, it says here that the probability of A is 0.5. So the probability of A is 0.5. The probability of B says it's also 0.5. And remember, in order to find the probability of compound probabilities, you just take the independent probabilities and multiply them. So that's 0.5 times 0.5, which for me shows as 0.25. Now I'm just going to leave this as a decimal because they gave us decimal values. But as percentages, remember, this is like saying, well, the probability of something happening here is 50%. The probability of the second independent event is also 50%. 50% times 50% is 25%, half of 50%. Okay, so that's compound probability because there's 2 different, well, it could be the same, but they're still independent events. And notice the word change on this one, by the way. Okay, we see the word and, where on the previous 2 slides we saw the word or when we were still looking at it as a simple event. Okay, so there's a huge difference between knowing the words and or and how they affect your probabilities. Okay, and indicates we're looking at compound events or compound probabilities, and or indicates we're still looking at simple probabilities or simple events. So what about this next one? Well, we see the probability of A there is 0.5. So again, we need that probability there. That's 50% that event A will happen. Event B shows 0.5 as well, so there's our 0.5 for that one. And then event C is also 0.5. So there's 0.5. Remember, for compound probabilities, we're just going to multiply these together and see what we get. So 0.5, you can use the calculator if you need to, but I know there's already 0.125 or 12.5%. Well, how do we get that? Well, I already knew that 0.5 times 0.5 is a fourth. So cut that in half and get an eighth, which, I mean, whether we're familiar with that or not doesn't matter because the calculator will do it. Would that be 0.125 or 12.5%? So using words and symbols, state your conjecture for the general rule for calculating probabilities for independent compound events. And this is what I'm going to put. You may put something else if it makes better sense to you, but this is what I'm going to put. So this is what I got. Find the probability of each independent event and multiply all those probabilities together. Okay? Just like we saw on this one. Well, I mean, they already gave us each of the independent probabilities, but we took each of them and multiplied them all together, just like we did with this first one as well. All right, number 1 here on this one, what is the sample space for rolling the number cube one time and then spinning the spinner? So I'm going to use a tree for this one of those old tree diagrams, okay? And I'll do it in this order, by the way. We'll look first at rolling the cube. So rolling the cube first. You can call it a dice if you want. Rolling the cube, we'll look at those different outcomes, and then we'll look at the spinner second. So there's our spinner. And this will produce our outcomes. At least we'll see if we can fit them all on there. Okay, so let's see, how much space do we got on this? Not a lot of space, but we'll figure it out. So rolling the number cube, right? And no trickery here. It's not like any of the values you cannot see on that dice are something other than 1 through 6. So we're just going to put these in. 1, 2, right, see if I can make this bigger. 1, 2, 3, 4, 5, and then 6. All right. Now, from what we can see on the spinner, we got 1, 2, 3, 4, 5 different colors on the spinner, right? So I'm going to start with red, because red is always nice. See if I can fit this on here anyways. But I'm going to have to write it small, because we're going to have to do a lot of these. Red, and then we got, I'll move clockwise around the circle there. Then purple, then blue, then yellow, then green. All right, so just starting with the 1. Let's say that you rolled a 1, okay? Well, from 1 you could get red, you can get purple, you can get blue, you could get yellow, or you could get green right there. So there's 5 different outcomes just for rolling the 1, right? But we should know that all of those are pretty much going to be the same for all of the different numbers we could roll from the dice. So this means I can duplicate this here just below the 1 with 2, right? 2 is going to have the same exact duplication right there. And then also 3 will have the same duplication. So let's put that on there. I have a little bit of overlap just because of the amount of space we have. 4 also will have the same exact values possible. We can kind of squeeze that one in. Let's see if we can make that work for 5 as well. So there's 5. And then finally, of course, we would also have the same exact values for number 6. Right, so we get all these different outcomes from here, and you may be thinking, well, that's a lot of outcomes. That's true, but it's not difficult for us, right? So let's see, for example, if you rolled a 1 and then red, you'd have the outcome of 1 and then red. So let's go and put that in there, 1 and then red. And you can see this, it's going to be a little time consuming, and this is kind of one of the reasons why we use the fundamental accounting principle for these, but we're going to have one different outcome for each of these, right? And now for these all, at least for these first 5, each of the outcomes is a 1 right there. It's just going to be a different color on those, so that'd be, the next one would be 1, and then purple. And then the next one would be 1 in blue. And then the next one would be 1 in yellow. And the final one would be 1 and green. And well, if you had listed your colors in a different order, you may end up with a different order of these, but the outcomes are still the same. That's kind of the crucial part. You forgot the 1 there. Okay, so those are our outcomes. We're just going to repeat this process for these other ones, for red, purple, blue, yellow, and green right here. But not only for 1, but, well, 3, 4, and 5 as well. So there we go. I got all mine. I just need to put the numbers in there, right? So there's 2 red, purple, blue, yellow, and green. And then with the next number, of course, would be 3 red, purple, blue, yellow, and green. And then for the next set, would have to roll 4 red, purple, blue, yellow, and green. And then for the next set, but rolling a 5 red, purple, blue, yellow, and green. And then our last set would be with 6. So 6 red, 6 purple, 6 blue, 6 yellow, and 6 green. These are our possible outcomes. This is our sample space. And I know that's kind of a small handwriting there. It's the best I can do to fit that in. But this will help us to figure out all of the outcomes. But not only all the outcomes, but it should help us to answer these next 2 questions. Now, did we have to do it like that? No, we did not. But it did ask for the sample space, so that's kind of what I did right there. Okay. So the first thing I'd say that we would want to do here is find out how many total outcomes there are. Now, if you count all those, there's 36. And if you use the fundamental counting principle, of course, you would have been able to figure that out pretty quick. There is 6 different possible outcomes by rolling the cube. There's 6 different colors on the spinner. Each of them is the same possibility of being spun as long as it's done randomly. And then you do 6 times 6, which is 36 total outcomes right there. So that's how we get 36 right there. And so on this one would say, on number 2, find the probability of landing on 6 and landing on purple with the spinner. So again, that's out of 36 different possibilities. So I would go down to the 6. I see 6 purples right here. That's one of the possible 36 outcomes. Okay. Now that's one way to do it. Again, using the sample space, and drawing your tree diagram, it's fun, but it's actually not necessary to do that. Here's why. Okay, because we can use essentially compound probabilities to solve this one, and it would have been much quicker without having to use the tree diagram. So we would look first at the probability of just 6, right? And then we would multiply that by the probability of, well, spinning purple. Because if we do it like this one, of course, it's just a little bit easier, but here's the thing. If you want the probability of rolling a 6, that's 6 possible outcomes on a cube like that, and 6 is one of those possible outcomes. And if you want the probability of spinning a purple, again, there's 6 possible colors on there, and purple's only one of them. Like I said before, for compound probabilities like this, you would just multiply the 2 probabilities in order to figure out your final probability on this one. And so it would say, well, in the denominator, I've got 6 times 6. So in my fraction, I got 6 times 6. The denominator is 36. In the numerator, we have 1 times 1, which is 1. So 1 over 36 would be our final answer on this one, at least as a fraction. Of course, if we needed to change that into a decimal or percent, which you may have to do on the assignment, then so be it, but I'm just going to keep this as a fraction. Okay, so the probability of 3 and tails, you roll a dice and then flip a coin. Okay, well, I guess this would be for a different problem, actually. But I can still use my compound probabilities to figure this one out, okay? So I know, at least for a dice anyways, if I wanted to roll a 3, okay, so that I'm just looking at the probability of tossing a 3 here. Well, that would be out of 6 possible outcomes, that's only one of them. Then I would also look at the probability of tossing a tails, which is the second event. Well, if I toss a coin, there's only 2 possible outcomes, heads or tails. Tails is one of them, and so to figure out the answer to this one, we're going to need to multiply these 2 fractions. Okay, and then whatever I get is my final answer. Of course, I'm still going to show this as a fraction, So I'll start in the numerators on this one. That's 1 times 1. That's easy. It's 1. And then in the denominator, 6 times 2, which is 12. So you got a 1/12 chance of not only rolling a 3, but also tossing a tails. So again, these are independent events, but we're now combining these. Now, it didn't use the word "and" in this, so you may want to be aware of that. But if you see a comma like this, we're looking at two different events. Of course, like on a cube, if it had purple on the cube, then it would have to say specifically that it does. So, but it did specify that here, rolling a 6 and landing on purple, which is right here. So there you go. That's a pretty good start for us right there. Not only with the sample space, and nice to see a tree diagram again, but finding these compound probabilities also. All right, for 4 through 6, I guess we'll use the compound random events. And I'm going to use the spinner that we used on that last problem. I know it didn't print on your paper, but that's okay. We're still going to use the same one. So number 4, toss a coin and get heads, and the spinner and get spinner at the right and get red. All right, well, again, we can even express our probability on this one like so. So P, remember that's the probability. We'd be looking for heads, so I'll just put H right there, and then also red. So heads and red. So of course would want to find the probability of both, but separately. So the probability of heads, and then I would also want the probability of spinning red on this one. Okay, we're just going to multiply those two values together. That's the whole idea with these compound events. So let's look at the probability of heads first. Well, there's only 2 outcomes when tossing a coin, and heads is only one of those, so that's 1/2. And then the probability of spinning red on this one looks like there's 6 colors again. Red is one of those, so we're going to multiply these together. That will tell us our final probability. So multiplying the two numerators, 1 times 1 is 1. Multiplying the two denominators, 2 times 6 is 12. So 1/12 would be the probability of tossing a heads and spinning red on this particular spinner. Now I'm kind of using straight fraction multiplication on that. You're always welcome to use your calculator to figure out that fraction multiplication if you'd like. Number 5, flip a coin 3 times and get tails every time. Okay, so this is, again, let's think about how this probability will work. Okay, so let's say, like saying on this tossing, you've got 3 different tosses, right? So we're going to look at this as toss 1, toss 2, and then toss 3. We should have enough space for that. All right, so there's our tosses, and it's saying we got to get tails every time. So toss 1 would be tails, toss 2 would be tails, and then toss 3 would be tails. Now, while we may be using the same coin, and we're going to assume that it's all a fair coin, on this one, these are all 3 different independent events, although they are the same event. Okay, it's just throwing up a coin. We're just doing it at different times. So it is considered a compound probability on this one. So if I wanted to figure out the actual probability on this one, I would find the probability of tails, and I would multiply that by the probability of tails and the probability of tails. Now this is not meant to be a trick question, but sometimes we can think about this in terms of, well, what's the probability of tossing a fair coin on the 20th toss, or in this case the 3rd toss, and still getting tails? Of course it's 1/2, right? So for each of these, the probability is always going to be 1/2, because when you toss a coin, you've only got 2 different outcomes. Only one of those is tails. So we're just going to take 1/2 and multiply it by itself pretty much 3 times. And yeah, if you remember how to use exponents on this, you could do that. Okay, so we're going to multiply these out. I'm going to multiply the numerators. 1 times 1 times 1 is 1. That's my numerator. All the denominators, 2 times 2 is 4, times 2 is 8, so I get 1/8. And that would be the probability of tossing a tails 3 times in a row with a fair coin. So number 6, pick a number from 1 to 5 and get 3, and choose a color from red, white, or blue and get blue. All right, so let's write our probability first. So it's the probability of getting a 3 from the numbers 1 through 5, and then looks like it was blue on that one, right? So it's the probability of picking 3 from the numbers 1 through 5, and then choosing blue from 3 different colors, right? So that means we'd be wanting to find the probability of choosing 3, and we look at these separately, and then also we'd look at the colors, right? So the probability of choosing blue on this, and all we're going to do is multiply these 2 probabilities to figure out our compound probability. So the probability of getting 3 from picking a number from 1 through 5, of course there's 5 different values to choose from, so it's out of 5, 3 is one of those, 1/5. What about the probability of blue? Well, the probability of blue, there's only 3 different colors there, so in my fraction, it's out of 3 different colors, and one of those is blue. So we're going to have to multiply these out to get our final fraction. In the numerator, I have 1 times 1, which is 1. In the denominator, 5 times 3 is 15. So it's 1/15th chance in this particular case. And you have to remember, this is not a dice. That it's not saying it's a dice. It's just choosing the numbers 1 through 5. And even the colors, we're not using the spinner for the colors on this. Okay, it's just these 3 colors that it gave us. So let's look at number 7. Choose purple, green, black, or silver bike and get purple. Then having 10, 18, 21, or 24 speeds, but get 18. Okay, well let's go and write out our probability here. So it's the probability of the color, which was purple. Make it purple. And then choosing the speed of the bike, which was 18, right? So choose a purple bike that's an 18 speed. Again, I don't know why you'd be choosing bikes randomly, but here we go. So we're going to figure out the probability first of choosing purple. And then we'll figure out the probability of choosing an 18 speed bike. And all we're going to do is multiply these together. That's it. Okay. So the probability of purple, again, as a fraction, purple is only one of the colors out of 1, 2, 3, 4 different colors on that one. So 1/4. And the probability of 18, 18 is one of those outcomes. How many is there? 1, 2, 3, 4 different speeds. And yeah, we just need to multiply these together. In the numerators, I'd have 1 times 1, which is 1. In the denominator, 4 times 4 is 16. And yeah, so we get 1/16th. It's a 1/16th chance of choosing a purple bike with that has 18 speeds. And again, just to reiterate this, just in case it asks for it on the assignment, if it asks for decimals or percentages, you should be able to do that. We had a full unit on that, essentially. So yeah, the expectation is that you are able to do that by now. Now that pretty much completes this assignment, but keep in mind, you guys, that we didn't actually do any of these experiments, okay? Which means that every one of these probabilities that we found in today's lesson here is all theoretical probabilities, not experimental. Remember, for it to be experimental, you actually have to do whatever the experiment is, and probably many times, and then you'll figure out your experimental probabilities, okay? But without actually doing these activities, these are all strictly theoretical probabilities. All right, so there's our objective. We can find the probability of simple, which is just pretty much one event happening at a time, and compound events, which is a combination of many independent events. So simple events, of course, we could say is independent event as well. We just look at it a little differently. And again, I don't use that vocabulary too often, at least with simple events, but more independent and compound type probabilities. Yeah, we use that type of vocabulary quite often.